out to the School of Science because they're having a research day, which I can't make, so I've been asked to actually give this video recording of that. So hello everyone, I'm at 37,000 feet right now, so I won't be with you. So what I'm going to do is give a quick overview though of my research interests, which of course are in the area of catalysis, and particularly the interface between physics, chemical engineering and also biosciences. So my group are really focused at the moment on the development of new functional materials. And those sorts of materials are particularly interested in trying to incorporate multiple functionalities to allow us to do cascade reactions. That is, transformations in which the product of a first reaction, so for example here, we have a molecule that goes in, interacts with an active site, comes out as a single product, and that product then goes and does a second reaction within another active site to make a second product. So a cascade. And these sorts of cascades are really important in the chemical sector. They allow us to access very high-value products and traditionally have been the realm of, for example, enzymes or organometallic catalysts. The heterogeneous community have lagged behind. So what we do is we try and take porous materials, inorganic oxides predominantly, that we functionalize with one kind of functionality. That functionality could, for example, be a metal. So here we're putting some platinum nanoparticles inside a mesopore, a small pore of material. And then we're putting some larger palladium nanoparticles on the second pore network. So in this case, it's macropores, bigger pores. So we've got materials where we have dual functionality introduced into them. And we can image those. So we do a lot of microscopy. And this is an example of electron tomography in collaboration with the University of Cambridge, Paul Midgley's group there in material science. And you can get atomic resolution in a three-dimensional structure and image a porous network. So that's really at the sort of the cutting edge of this sort of microscopy imaging here. And once you've made these materials, of course, you use them as catalysts. And so the sorts of transformations are where you take, for example, an alcohol. It undergoes one reaction in one of the pore networks, diffuses through into the second pore network, and undergoes a second catalytic reaction. So in one pot, in one flask, with one nanoparticle, you can do two reaction steps. And because you have these two active sites very close to each other, you can control the sequence and also the rate at which those molecules are transferred between the two catalytic sites. And it also allows you to introduce, for example, incompatible catalysts. Traditionally, if you pour sulfuric acid and sodium hydroxide into a beaker, they will react with each other and not with the molecule you want to react with. Here, we can pin, for example, an acid catalyst in one site, a basic catalyst in another, and stop them interfering with each other. Okay, so we can make acid-base analogues. So that's sort of chemistry. As I said before, it's typically for high-value materials. So in this case, we're looking at something, for example, benzyl alcohol or cinnamon alcohol that you can obtain from biomass that goes to a first step and a second step, and you can make, for example, additives for fragrances and foods, sweeteners, etc. Okay, so that's one side of the material synthesis. The other thing we do is spectroscopy. And basically that involves shining light on materials and trying to characterize them, trying to characterize both the nature of the active site, particularly during a reaction, and also the molecules themselves as they undergo that transformation. So here's some time-resolved measurements where we, for example, fire in X-rays, typically done at a synchrotron. So we fire X-rays in to interrogate our catalyst, for example, the oxidation state or the particle size. We simultaneously bounce infrared light off the surface of the nanoparticle, so we can characterize the adsorbate on the surface of a catalyst, and we can track the transformation on the surface, and then we'll maybe hook up a mass spectrometer at the end so we can work out the product yield. And we do these sorts of measurements under dynamic conditions. So, for example, we can put in two reactants. For example, we can put oxygen or an alcohol. We can oscillate those very quickly. Each of these data points is a sub-second, so we can get sub-second resolution on the oxidation state, morphology, composition of a material during a reaction. So this, for example, is a gas phase case. Here's an example of doing something on a single crystal. So this is more detailed mechanistic work very much at the physics interface, where we can put a molecule onto a surface and we can see it transform through various steps by using, in this case, again, X-rays. So these peaks here represent the chemical state of a different species on a catalyst surface as we're heating it up. We can also do things in the solution phase. So a lot of high-value products are associated with liquid phase transformations in the chemical sector, not gas phase. So here's an example of a reaction, which is an oxidation where we take a molecule called HMF and turn it through to FDCA. That's basically a bio-derived polymer that can replace things like PET plastic bottles. And again, so we can take a catalyst, and that catalyst we can put inside a beaker, and we can interrogate that catalyst with light to look at its oxidation state and particle size, etc., as the reaction occurs. And so that really allows us to get a handle on what the true nature of the active site is, and therefore hopefully engineer more of those and stabilize them. Okay, so in terms of other research interests that my group's looking at, we've worked for many years on alloys, particularly both single crystal and nanoparticle alloys, and trying to understand the relationship, again, as I said earlier, between structure and function. That's a very hard thing to decouple, and it requires precise control over the shape and size and composition of the materials. So nanomaterials methodologies to prepare materials is crucial in this. We also do a little bit of work, not quite as much in computational chemistry, and that's really where we like to collaborate. So we have done some DFT, atomistic, very high-level calculations to, for example, look at the adsorption of a molecule on a catalytic nanoparticle and to understand how the strength of that changes as a function of coadsorbates. Here's some examples of gold nanoparticles which have oxygen atoms nearby, and depending on where you put the oxygen atoms, it controls the adsorption geometry and the strength, the energy with which these molecules are bound to the surface, and therefore the chemistry that they do. We also have done some calculations in the organometallic sector. So here's looking at some ligands, and by understanding the electronic properties of those ligands, we can work out how they coordinate to a palladium center and how that then controls, for example, Heck and Suzuki cross-couplings. We also do a little bit of work in what I guess I would call reaction engineering space. We're not chemical engineers, but we love to work with them. And here looking at trying to take reactions from the beaker, the batch regime, into the flow realm. Again, doing a cascade where we have two packed beds, one with a catalyst, one kind, for example, palladium and platinum, and we can do a two-step reaction in flow, which allows us to continuously manufacture a high-value chemical, rather than having to do a reaction over a long period of time and then try and separate out the catalyst from the valuable product. Okay. Photocatalysis has been working in for a little while now, and we're particularly interested again in the idea of trying to make fuels, so solar fuels with sunlight as the energy source, and trying to trap that solar energy into a chemical energy source. Energy carrier. In this case, taking CO2 through to either methane or methanol, or, in fact, going to chemical manufacturing from that. In principle, you can take CO2 and transform it not just to methanol or methane, energy carriers, but also into, for example, olefins, the C2s, C3s. And that's a much smaller market of higher value products to try and tap into. So trying to replace the global petroleum-derived fuel base is a very, very long distant possibility. Trying to replace the sources of olefins is actually a much smaller and easier target to achieve, a much lower hanging fruit. Then finally, we're interested in, I guess, more the sort of solid state condensed matter questions associated with the formation of defects and the roles they play in catalysis, and particularly the role that they play in pinning individual atoms. So there's a huge amount of interest in trying to move towards more earth-abundant catalysts by, for example, reducing the precious metal content that goes in traditional industrial processes. So it's called precious metal thrifting, traditionally. So here we've been able to take a single palladium atom, by pinning it at defects in an oxide lattice, we can actually dramatically enhance the activity of each of those atoms. And so that allows you to bring costs down dramatically and get better control over selectivity. That's been done. Thank you.